There's a very nice relationship between geometry and algebra that you can use to understand lots of properties of the trig functions. It is in terms of the unit circle as the framework for applying the general angle results that we talked about last time. The unit circle is just a circle of radius 1 centered at the origin. Since it is extra, there are extra properties that are asked of it in a general circle, both where its center is and what its radius is. It has special properties that come from that. For example, there was the arc length formula that worked for general circles of radius r to relate the arc length to the radius and the measure of the angle. If the radius is 1, then the arc length is immediately, not scaled at all, just equal to the radian measure of the angle. Here's a picture that shows that. This is the unit circle. Notice that from 0, 0, we're going 1 unit to the right, to the left, up and down, and measuring the angle theta, so that the angle theta, measured in radians for angle measure, is immediately linked to this distance, where the distance s is given in length units that is relative to the 1 unit that is the radius of the circle. So you can apply this to come up with a point at in any quadrant. Let's put it in quadrant 2. Here we're going all the way around t radians, so a distance of t units, and we end up with a point on the unit circle with coordinates point A and B. Well, you know what to do when you've got a point on the circle determining what could be the hypotenuse of a triangle. To get the reference triangle and the reference angle out, you drop a perpendicular. There's a perpendicular, and with this perpendicular, the coordinates of the point on the circle, A, B, have immediate relation with the trig function values. Remember the ratio definitions for sine and cosine. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And since the hypotenuse is the radius of the unit circle of length 1, that means that the denominators in those ratio definitions are 1, and the numerators are the actual values of the trig functions. In short, this point that we've got AB on the unit circle has coordinates that are immediately values of the sine and cosine. Sine of the value t, which is the radian measure of the angle, is the y-coordinate of that point. That's the coordinate b, the second coordinate. And a, the x-coordinate, is the side adjacent in that triangle that gives the cosine of the angle. So just from drawing a triangle and a point on the triangle, you can read off values of the trig functions directly as the coordinates of that point. Here's an example. Suppose you've got a real number and a point on the unit circle that corresponds to that real number as a radian measure of the angle, or as the arc length going around the unit circle. We can calculate all 6 trig functions just from that geometry. We have immediately that the point's coordinates A, B are the values of the sine and cosine. So sine is the y-coordinate, that was the number minus 15/4, and cosine was the x-coordinate, the value A, that was 1/4. Well, we know how sine and cosine relate to values of other trig functions. If we've got those as the values for sine and cosine, tangent is sine divided by cosine. That's b divided by a. That's the value, the y-coordinate divided by the x-coordinate value. You could simplify that compound fraction, invert and multiply, and the 4's cancel. It's just minus root 15. You can get cosecant as the reciprocal of the sine, the reciprocal of minus 15/4. That's the y-coordinate, the sine of that number, minus 4/15. And then that trick of rationalizing the denominator, we can write that as minus 4 root 15 over 15. Secant, the reciprocal of cosine, so the reciprocal of the x-coordinate is 1 over a fourth, that's 4. What do we have? Sine, cosine, immediately, tangent, cosecant, secant. I guess I still need cotangent. And cotangent is the reciprocal of tangent, so instead of dividing sine by cosine, we'll divide cosine by sine, divide the x-coordinate by the y-coordinate. That puts, with a 1/4 and minus 15/4, the 4's cancel, or invert and multiply and get rid of them, and it's minus 1 over root 15. And again, rationalizing the denominator, that's the 6th trig function. Let's try another example. How about if we're given a value for the secant function and an extra piece of information that the sine is positive. Sine is bigger than 0. Let's see what that says about values of the other trig functions. Well, we could draw a picture to keep track of that. Now, I've been thinking in terms of the unit circle, but maybe it's a little easier to use the given value for secant theta to label it a little bit differently. Secant is the reciprocal of cosine. Cosine is side adjacent over hypotenuse. So secant would be hypotenuse over side adjacent. Let's draw in a triangle that makes that happen. We'll draw x squared plus y squared equals 25 to be a circle of radius 5. So this distance is 5 units. That distance is 5 units, and now I'd like to go 2 units back to be the x-coordinate to get the side adjacent that would belong in that ratio. So let's do some numbers to keep track of that. Secant is 5 halves, minus 5 over minus 2. The radius is the positive value by convention, so r is plus 5, a is minus 2. And I've got those two values determined. We can get b out and use the Pythagorean theorem. Now from the Pythagorean theorem, we've got a squared plus b squared equals r squared. That's going to give a value for b squared out, and when you take the square root, it could be positive or it could be negative. In this case, we know that we want to take the positive square root. Let me show you why. Back. Look at the picture again. We want to take the positive square root because the value for sine theta bigger than 0 guarantees that the angle that we draw in is going to have terminal side in quadrant 2. Quadrant 2 has a negative x-coordinate and a positive y-coordinate, so the b value has to be positive. Back where we were. So let's solve for b, plugging in minus 2 for a, plugging in 5 for r, and out comes a value for b of b squared is 21. b is the positive square root of 21. Now let's use that in the ratio definitions of the other trig functions. Now we've got all the pieces to put those together. Sine is b over r. Sine is opposite over hypotenuse. So we've got values we can use for sine. Cosine is adjacent over hypotenuse, in this case minus 2 over 5. Tangent we'll do directly as opposite over adjacent. 21 over minus 2. Now if you'd like, you can write that ratio of numbers as a negative and put the negative out front. That's probably the way you'll see it reported. Cosecant's the reciprocal of sine, so instead of b over r, it's r over b. Flip root 21 over 5 and then rationalize the denominator to get cosecant. Cotangent's the reciprocal of tangent. Let's do that one. So we had tangent, so we've got cotangent. Is that everything? Sine, cosine, tangent, cosecant, cotangent. I didn't tell you secant in this screen, but remember that's how the problem started. The value of secant was what was given. So we found everything else from the right triangle geometry inside that unit circle. Now let's think about facts about the trig functions that follow immediately, geometrically, from facts about the geometry of the unit circle. What we've got is a point that is always on the unit circle as a point on the terminal side of the angle. Since it's always on the unit circle, the value of the coordinates of the point AB is bound. It can't ever get bigger than 1. It can't ever get less than -1 on the x-axis. It can't ever get bigger than 1 or smaller than -1 on the y-axis. So let's see what that says about values of the trig functions. The domain of the sine function is the set of all real numbers. There's no number in this picture that you can't spin around and assign an ordered pair on the circle to. Any value works, any value is acceptable, any values in the domain. The domain of the cosine function works for any value. For the tangent function, there's a little problem just because tangent with the quotient identity, tangent is sine divided by cosine. If it turns out that cosine is 0, then you're trying to divide by 0, and that leaves the value of the tangent function undefined. That happens at multiples of 90 degrees or pi over 2 radians. Secant function, the same problem. Secant's the reciprocal of cosine, so if the cosine on the bottom happens to be 0, you've got problems. The range for the trig functions for sine, it is guaranteed that it is less than or equal to 1 in absolute value, because the a coordinate of the point on the unit circle is between -1 and 1. Similarly, the y coordinate is between -1 and 1, and the y coordinate being there is the restriction that tells you about the sine function. The x coordinate is the restriction that tells you about the cosine function. So the fact that you've got them trapped between -1 and 1 tells you what the range is of the sine and cosine. It is guaranteed to be the closed interval from -1 to 1 in either case. How does it work for the other trig functions? Cosecant's the reciprocal of sine. Think about it this way. If you've got a number less than 1, its reciprocal is guaranteed to be bigger than 1. So less than 1 in absolute value guarantees that the reciprocal is bigger than or equal to 1 in absolute value. So the range of the cosecant function and the range of the secant function are values guaranteed to lie outside that interval from -1 to 1. Equals, okay, the reciprocal of a value where sine is 1 is a value where cosecant would be 1. The reciprocal of a value where cosine is -1 would be a value where secant is -1. But can't get inside for the cosecant or the secant function. The tangent function, on the other hand, can take on any value. We're going to have an interesting applet to try out where you watch the values of the trig functions generated as you drag a point around the unit circle, and you observe values of tangent and then the reciprocal cotangent taking on any value from -infinity to infinity. The last property to note about the trig functions is their periodicity. Saying that it's periodic, think about what periodic means just in a colloquial way. Periodic means that things happen over and over again. They cycle. They go through the same set of values over and over again. And a periodic function does that. You specify what the period is, say value p, then when you go p units further on from a value of the function, going those p units further on steps you through a sequence of values back to a value at before you started that step. So f of theta plus p matches what you had before you shifted it by that distance p. F of theta plus p matches f of theta. Trig functions are that way, and a reason to see why is that when you measure an angle around the unit circle, whether you go an extra 2 pi radians, 360 degrees, puts you at the same terminal side. It doesn't affect what the coordinates of the point would be. In particular, the y-coordinate is the same. The sine function is the same for theta as it is for theta plus 2 pi. Cosine's the same for theta as it is for theta plus 2 pi. These first two rows of the table say, yes, it works for sine and cosine, and it also works for their reciprocals. Notice that tangent has a period a little bit smaller. Instead of 2 pi, tangent's period is pi. The reason for that is in quadrant 1, you've got, for the tangent function, a ratio of 2 positive numbers, and in quadrant 3, you could do it as a ratio of 2 negative numbers, but that's still a positive number back. So going from quadrant 1 to quadrant 3 takes you from a positive value of tangent to a corresponding positive value of tangent. Only pi units for the angle measure that's all it takes to get back to a value of tangent that matches what it was before. So sine, cosine, and their reciprocals are periodic of period 2 pi. Tangent and its reciprocal, tangent and cotangent, are periodic of period pi. One more fact about trig functions that you can interpret immediately from how the unit circle works are even in odd properties. The sine function is the y-coordinate. If you go down or up, you're changing the y-coordinate of a point on the unit circle. It's positive or negative. So sine of minus theta and sine of theta differ in sign, S-I-G-N. One of them's positive, one of them's negative. That makes sine an odd function. Cosine is the x-coordinate. The x-coordinate's the same whether you're measuring theta or minus theta. You either go up or down. In either case, you go out in the x direction, on the x-axis, the same horizontal distance. That means that cosine of minus theta and cosine of theta have the same value. That means cosine is an even function. Cosine's even, so is its reciprocal. Sine is odd, so is sine's reciprocal. Tangent is an odd function divided by an even function, sine divided by cosine. That's an odd function back. Tangent has that symmetry, and since tangent is an odd function, cotangent is also an odd function. Thinking about those properties of the trig functions can sometimes make it easier to simplify expressions involving the trig functions so that they aren't as tangled up as they might be otherwise.